This is General Chemistry. Cover the topic of gas, Part 10. Today we will be looking at real gas. Before we talk about real gas or non-ideal gas, let's point out a couple of things that we learned earlier from kinetic molecular theory or KMT. KMT helps us understand the behavior of gas, especially in ideal situation. In KMT, gas molecules are so tiny, they take up pretty much no volume, especially when compared with the volume of the whole container. And these gas molecules experience no intermolecular forces between one another. But in reality, gas molecules occupy some space, so they do have some volume. And these gas molecules may interact with one another, so they have intermolecular forces. And these real gases tend to deviate from the ideal behavior, especially at high pressure and low temperature. At high pressure, gas can be compressed, and the gas molecule can move more closely to one another. And in this smaller space, the volume of gas molecules will become more important. And that makes the real gas deviate from the first point of the KMT that we just talked about a little bit earlier. And when the molecules are closer to one another, the intermolecular forces or intermolecular attractions between these molecules will become more significant. And that makes the real gas deviate from the second point of the KMT that we also just talked about a little bit earlier. And for the low temperature, when it's cold, the gas molecules will move more slowly. They spend more time being closer to one another. So the intermolecular forces between them will become more significant too. There is also another aspect of real gas that we should talk about, and that is how they look like in graphs. Please be aware that the gases plotted here are at the same amount and at the same temperature. One of the most common graphs is the plot between PV and P, the pressure of the gases. Ideal gas will give a linear plot at one fixed value. And that makes sense. For the ideal gas, we use PV equal to nRT. Since R is a constant and N and T are fixed, it means that nRT will stay constant throughout. That means PV will have only one single value. But for real gases, they can vary a lot, and they are usually not fixed on one single value. PV and P is actually not the only common graph for the real gas. Sometimes you may see the graph between PV over RT and P, the pressure of gases. Again, for the ideal gas, it will be a linear plot at a single value. But for the real gases, they can vary. And sometimes they may give you the graph between PV over nRT and P, the pressure of the gases. Still the same idea. For the ideal gas, it will be a linear plot, fixed on one single value. But for real gases, they can vary. There is also another type of graph that we should be looking at. In this case, they zoom into the little box. That means they are looking at the graph at relatively low pressures. And we may see something a little bit different. At low pressures, the plots of ideal gas and real gases can be linear. But there is at least one difference. For the ideal gas, its linear plot is still fixed at one single value. But that is not the case for real gases. Let's say we have the graph PV and P for hydrogen gas, oxygen gas, carbon dioxide gas, and ideal gas. If you take a look at the graph on the right for the low pressure, we can see that hydrogen gas, which has the smallest molecule here, will behave most closely to the ideal gas. But for carbon dioxide gas, which is the molecule with a larger volume, will deviate more from the ideal gas. Now we will try to focus on the quantitative aspect of the real gas. We will be looking at real gas equation. There are actually a few equations out there for real gas, but the most common one is probably Van der Waals equation. And this is how Van der Waals equation look like. It looked quite similar to PV equal to nRT from the ideal gas. But since it's for real gases, so we have corrected pressure and corrected volume. A and B there are sometimes called Van der Waals constants. And as you can see from the values listed here, they are unique for each gas. Alright, so those are the key concepts for the real gas. Now let's try to take a look at a practice question. For this one, calculate the pressure in atm of 5 mole of methane gas in 4-liter container at 57 Celsius using A. the ideal gas equation and B. the Van der Waals equation. And they give us the Van der Waals constants for the methane gas A and B. Let's start with part A, the ideal gas equation. We know that for the ideal gas, we have to use PV equal to nRT. And they're looking for P, which gonna be equal to nRT over V. Let's try plug the values in. N is 5 mole. R is 0.082 liter atm per mole Kelvin. T is 57 Celsius, which is 330 Kelvin. And V is 4 liter. Alright, so to calculate that out, we should get about 33.825 atm for the ideal gas. Now let's try using Van der Waals equation, part B. For the Van der Waals equation, we will use P plus A n square over V square times V minus NB equal to nRT. We will get P plus A is 2.25, N, which is mole, is 5 square over V is 4 liter square, and then we times V, which is 4 liter, minus N, which is 5 mole, and then B, which is 0.0428. Alright, and that's gonna be equal to N, which is 5 mole, R, which is 0.082 liter atm per mole Kelvin, and T is 57 plus 273, and it's gonna be 330 Kelvin. Here we will get P plus 3.5156 times 4 minus 0.214, and that's gonna be equal to 135.3. And then we should have P plus 3.5156 equal to 35.73, and that's gonna give P to be equal to 32.221 atm. So we can see that if we use the ideal gas equation, we will get the pressure to be 33.825 atm. And when we use Van der Waals equation for real gas, we're gonna get slightly lower value, which is 32.221 atm for this case. Alright, let's try another question then. For this one, which of the following statements is false? For the first statement, molecules of ammonia gas have no intermolecular attractions at high pressures and low temperatures. At high pressures and low temperature, the molecules will behave more like real gas, which means the intermolecular attractions or intermolecular forces will become more significant. So, this statement is false. For the second statement, sulfur dioxide gas is expected to behave more ideally than carbon dioxide gas. Well, let's take a look at this one a little bit more carefully. Remember that there are at least two things that make real gas molecules different from the ideal gas. First, the real gas molecules have volume. So the gas with larger molecules will behave more like a real gas. And between sulfur dioxide gas, SO2, and carbon dioxide gas, CO2, SO2 is larger. If you look at the periodic table, you can see that sulfur is larger than carbon dioxide. So SO2 will behave more like a real gas than carbon dioxide. And another difference is intermolecular forces. For sulfur dioxide, one way to write the chemical structure is this with lone pair. Some may draw the chemical structure of SO2 slightly different from this, but in either case, SO2 is a bent and polar molecule, and its major intermolecular force would be dipole-dipole. But for CO2, the chemical structure would look like this. So CO2 is a linear, non-polar molecule, and its major intermolecular force would be London dispersion force, which means SO2 will behave more closely to the real gas than CO2. So, based on the volume and intermolecular forces, SO2 will behave more like a real gas than carbon dioxide gas. And it means that the second statement is false. And for the third statement, real gas molecules have significant kinetic energy, and ideal gas molecules have no kinetic energy. We can just look at that part. The ideal gas molecule have no kinetic energy. This is totally false. Based on the kinetic molecular theory or KMT, even ideal gas molecules have kinetic energy too. So, this third statement is false. Since first statement is false, second statement is false, and third statement is false too, we're gonna choose D as the answer here.